So what we're going to talk about today in this video is rigid body momentum. You've already dealt with it with particles, and in particles we worried about momentum associated with just mass, but now it's mass and shape. So I'll do about 4 examples that I think are kind of helpful. Look at a few problems with momentum, angular and linear momentum, of course. So both, it's more important, angular momentum is much more important in this chapter than it was with the particles, because now things can spin around and have shape. Remember, it's still the same as before, but only difference is it has shape. So let's take an example here where we have a frame, which is in dark blue, that is sliding between 2 tracks and their wheels that hold the frame in place. It's released from rest, and you're asked to find the omega at point O. And so what's going to happen in terms of the motion is that it moves down and reaches this bottom point and then rotates through. And what you're looking for is the omega defined by that green arrow. To do this, first I need to know what the linear velocity is once it reaches point O. So if I start at the top and I release it, it's going to travel in a linear fashion. So there's no omega at this part of the problem. And so I can do this as an energy problem. And if I do that, still the center of mass, and the center of masses translated a distance a. So in terms of where I start, I have here first of all T1, which is the initial kinetic energy, which is 0, and V1 because I'm going to define my datum in such a way that I can get away with this being 0. So that's my 0. And so M frame GA. When it's at the very bottom, it's all kinetic energy and no potential. So it'll be 1/2 mass of frame times velocity final squared. And you're familiar with this. You've seen this in enough problems already, but the final velocity is square root 2GA, or 2GH as we've normally written it. Okay, so that's the first part of the problem. Now let's look at the rotation. So what's happening is that the linear motion is now translated or transferred to a rotational motion. And so I need to first calculate all of the inertial moments of inertia. So what I'll do is first I'll define it with respect to a long slender rod, and then I'm going to translate it to the center of mass here. So the center of mass here is going to be A over 2 away, and that's G. That's not a great drawing, but you get the idea. Since there's 4 bars, that would be I frame equals 4 times I side. And so I about O is then going to be the distance that it takes to go from G, which is A over 2 again, and A over 2 again, to O. So I have 2 parallel axis theorems that I'm going to use, one here, and I multiply by 4 to get all 4 bars. And I end up with 5/6 ma squared, or 1.11 kilogram meter squared. Short time, rotation, angular momentum. This is how I know this is that kind of problem. So the initial angular momentum equals the final angular momentum. It occurs over short time. So the argument is that there's T1, T2 is 0, and so any impulse would be 0. You then have the linear term, which was the linear momentum mv, acting over a moment arm a over 2, and then you have I naught omega, and you can calculate all that, and you end up with 4.69 rads per second. Here's another problem. So similar kind of problem-ish. I've got a wheel that's rolling down a ramp, and despite the drawing, it's in contact at this point, and it's in no slip. And you have a velocity that's given of 1.7 meters per second at the initial stage, inner radius of 80 millimeters, outer radius of 140 millimeters, a theta of 12 degrees. Mass of the wheel is given as 58 kilograms. The radius of gyration is 92 millimeters. And T, which is this, is 82 newtons. Now the only difference between part A and part B is where T is applied. And you're asked to find how long it takes for this to stop. And since it's a time force velocity problem or time moment velocity problem, you're going to end up with a angular or linear momentum problem. So let's start on this. So good practice is always to draw out the axes right here. And I've done that finally, x, y, and my positive is counterclockwise. In here, I have the tension, I have weight, and in orange are these two forces, and these I put in orange for a reason I'll show in a second. I have a double RI, but it's just RI and R naught. So H1 is mass of the wheel, radius of gyration of the wheel, plus the associated shift, which is going to be from the outer radius, or from the center to the outer radius, so that's a parallel axis there. The impulse delivered is going to come from the weight and the tension. And here the tension is R outer, R inner. The weight is just going to be the component acting in the sine theta direction. That's the only one that does a moment. And you'll notice that the two orange forces actually act through the point of contact, and so don't play a role in the moments. So H1 plus impulse is equal to 0, and I end up with a positive value of 13.4 seconds. So 13.4 seconds to stop if t is up here. If I shift t down, everything's exactly the same except here. That sign flips from positive to negative. All the other terms are exactly the same. It's still negative moments, all of that. And I end up with a result of minus 1.69 seconds. So what that tells me is that applying the tension there does not stop the wheel. So kind of fun problem just to show some of that. Okay, and we can do more complex types of geometries, and we're looking at very complex geometries in a relatively simple way. And so here you have a mass that is attached to the end of this orange cord. The other end of the orange cord is a force F, which is acting downward, and you're given the mass of the crate, I'm going to call it, is 12 kilograms. The force that's applied is 67 newtons. Mass of the pulley is 55 newtons. Mass of the crate is 8 kilograms. Ri is 130 millimeters, so that's the inner radius. Ro is 234 millimeters, and the radius of gyration is 172 millimeters. So in order to solve this, what I'm going to do is I'm going to look at it as a free body diagram, of course, but when I do that, I'm going to break it up into two parts. And again, good practice. At this point, this is something you really should do as a second nature. Just draw your axes. You'll find it's really useful. I find it's useful because I always make mistakes and I forget things. But I have force acting downward, I have tension acting downward, and I have the reaction forces at the pin. Now I'm going to get rid of the reaction forces at the pin because I'm going to say, well, I'm going to take moments about the center O, and I'll just have force and tension. I'll have omega, which is defined here, and that's a positive rotation for T, or for the pulley. So if I do that, it's really a angular momentum problem where the initial angular momentum plus the moment, or the impulse, the angular impulse delivered over T1, T2 equals final angular momentum. And so that's F times R outer times the time it takes T times R inner, and that's negative because it's going to be in the clockwise direction, is equal to moment of inertia mkg squared times omega. And remember, this starts at rest, so this term goes to 0. For the second term, I have tension and weight, and I've got velocity, I'm assuming upward, and so I've got L01, L02, T1, T2, F0, dt. So initial angular momentum, which is, or linear momentum, which is 0, initial impulse, which is going to come from the tension and the mass of the crate, gt, and then finally the final linear impulse, linear momentum, sorry, I keep tripping over my tongue. And the other thing I got to recognize is this, which is I can write the velocity in terms of the pulley angular velocity as Ri omega. Now, it's not hard because I've got capital T tension, which is one unknown, omega, which is the other unknown. T is given all of the rest of the terms. You had T of 2.5 seconds. You have 118 newtons and 0.51 rads per second. I used SMath Desktop for this solution. I could have done it any number of different ways. It's just there's not much once you write out the terms. So the final example I'm going to do is one that's a little bit difficult to do in class. I wouldn't actually do it at all. I have a model of an amusement park ride, and the cars that are at the end of each of these arms, and I'll show those in a second, rotate 90 degrees while the center axis rotates. What is the increase in angular velocity between A and B? So for this, it's sort of rotating in a counterclockwise direction. You see L, which is defined to the end of the rod, and at the end of the rod, I have placed 3 cars. Those cars are in position A as shown, so parallel to the floor, and for the second part B are normal to the floor. The cars themselves have a mass m and a radius of r. So mass of the car, length of the rod is 800 millimeters. L is the L of the car is 375 millimeters. It's a model. R is equal to 92 millimeters. And omega is 130 RPM. So it's not rads per second in this particular problem. That's just something you do when you're bored and you want to make unit conversion part of the problem. IZZ is 0.03 kilogram meter squared. So if I take that same problem and I rotate it and look down on it, I have the center axes and I have the 3 legs. And again, I've made sure to define my positive direction right here with x, y, and the rotation. So in position A, I have this. So I have h naught 1, which is 3 cars times the moment of inertia of each of the cars plus the parallel axis theorem in order to get the final moment of inertia for the system. I also have added into this IZZ, which was given at the beginning of the problem because that's part of it. When I rotate into orientation 2, same thing, but now because it's in this orientation, and you remember that the definition of moment of inertia is dependent only on geometry, not any absolute value. You can't look it up in a table and say this value for this car is always this. It's going to depend on how the car is oriented. And so for a cylinder oriented in this way, it essentially becomes that of a disk. And that's what you see right here. And then you have, again, the parallel axis theorem plus IZZ. You get the 2 h naughts. And after that, what I'm going to do is say that the initial angular momentum is equal to the final angular momentum. I'm going to assume this occurs over a very short time, very quickly, and I get omega f, which I probably shouldn't put 2 equal signs, is equal to 131.9 RPM. Now, when I did this, I calculated in rads per second, of course, and then translated it back to RPM. Now, in terms of what that means is I ended up with a percent change between the final angular velocity and the initial angular velocity of 1.2%. Not a lot, but it's just useful to know. Force velocity time. These are force velocity time problems, and you should get really used to the idea of force velocity time, moment, angular velocity time. But once you see that, you should recognize it immediately. It's the problem themselves, the problems themselves are not difficult. I didn't do any vector problems. We can do vector problems, and I've done some of them previously in the particle section. Those are a little bit more complex, but they're only complex because you need to understand what the motion is. So for example, in that last example, I couldn't do it in lecture because I can't really draw that motion really well, and it's very confusing to try and explain it in lecture. However, once you see the motion, it's easier to do the problem. And really, that's the trick in this course. This is really the trick in this particular chapter. Understand what the motion is. And what that kind of comes down to is sort of a standard recommendation: practice, practice, practice. Thank you very much. And yeah, I'm kind of bored. So some of the numbers look kind of weird, and I wouldn't normally use them on an example, but this is because I